to lesson 3, which is assessing normality. The term normality comes from the normal distribution, which is one of the most important concepts we learn about in statistics. You don't know yet what a probability distribution is, but you will as the course progresses. The normal distribution is a continuous probability distribution that is symmetric and bell-shaped. Looks like this. This normal distribution is based on two things, the standard deviation and mean, which are examples of measures of spread, which are the two most important things you can know about your data. The normal distribution is the key concept of advanced statistics. It is very important throughout any stats course, and especially ours. We'll get started on this topic in this lesson by learning how to assess normality. That means to determine whether or not the data you have comes from a normally distributed population. We're going to learn how to do that with a statistical graph and also something called the empirical rule or range rule of thumb. They really mean the same thing. Why is this important? Well, if we know whether or not the data we're dealing with is normally distributed, that will greatly impact what methods we use later in this course to find probabilities. The first technique for assessing normality is to use a graph. This is easiest with a histogram. When we look at a histogram, we're looking for it to start low, end low, have a roughly symmetric shape, and peak in the middle with limited gaps. Each of these graphs here on the right show histograms of data that comes from a normally distributed population. Now there is some gray area in statistics, so not all of these answers are going to be easy, but the examples we show you, we do try to be a little bit more dramatic. This example is clearly not symmetric. You see that it ends low, and it does have a peak, but it starts relatively high, and it's certainly not symmetric. So if I was judging off of this histogram, I would say this data is not normal, meaning it does not come from a normally distributed population. Now this one's a little bit tougher here on the right. It starts low, it ends low, I don't see any gaps, and it has a peak in the middle. It's not perfectly symmetric, but it is somewhat symmetric, and I think that's enough to go on to say that this is probably normal. Now you may be thinking, this isn't very scientific, we're just looking and guessing, and that's not true. We are making a very educated decision, but this does show us the need for something more formulaic, which we call the empirical rule. And what the empirical rule does is it mathematically determines whether or not we're dealing with a normally distributed set of data. Here's what the rule says. It says that 68% of data within a population should lie within one standard deviation of the mean. 95% of the data should lie within 2 standard deviations of the mean. That part's what I call the range rule of thumb. And that 99.7% of data should lie within 3 standard deviations of the mean. So if we're able to find the mean and standard deviation of a data set, we can set up these 3 ranges and see whether or not our data comes close to these percentages. So here's our data set, and it is pretty large. To determine the mean and standard deviation, I'm going to go to Desmos and put all of this data into my table. All right, now that I've got all that data entered in, I'm going to go down to the next tab, go to Functions, Stats, and Standard Deviation. And I'll put in x1 to get my standard deviation of 3.76. And my mean, which is denoted x bar, I can find the same way and get 17.28. So now that I know my mean and standard deviation, again, x bar, this symbol means mean, and s means standard deviation. Now that I know those, I can start setting up these ranges. Since 68% of the data should be within 1 standard deviation of the mean, the range that represents things within 1 standard deviation of the mean is x bar minus s, the mean minus 1 standard deviation, and x bar plus s, the mean plus 1 standard deviation. So if I plug in what I know, I can then simplify to find the range. I'll go back to my graphing calculator, and I get 13.52, and just changing that minus to a plus, I get 21.04. Now these numbers, 13.52 and 21.04, are the bottom and top of the range of numbers that are within 1 standard deviation of the mean. So now we can look at our data set and see how many of these data values lie in this range. Well, the first one I see that does it is 13.7. Then this entire row lies within those 2 numbers, as does this row, as does this row, and this value as well. Since these rows are 10 wide, that means we have 10, 20, 30, 1, 32 data values in this range. And since there's 1, 2, 3, 4, 5 rows, that's 32 out of the 50 data values fall within one standard deviation of the mean, or 64%, which we'll eventually compare to what was supposed to be within this range. Now that wasn't enough. Remember, the empirical rule has 3 parts, and we've only done one of them. The next part says 95% of the data lies within 2 standard deviations. Lying within 2 standard deviations means if I subtract 2 or add 2 standard deviations from the mean, I should see the lowest and greatest possible numbers that fit this description. My mean and standard deviation are still the same, so I can plug those right back into this formula. We'll go back to Desmos, and most of this is already typed in for us. We'll just change this to a -2 and then put parentheses around the 3.76. And we get an answer of 9.76. And if I just change this to a plus in the middle, I get the other half, 24.8. Now this range is centered around the mean, which is the same mean from our previous range. So this is just a wider version of this previous range. So all of these data values that fit into the first range, they'll also fit into the second range. However, additionally, we'll find some other data values that also fit. It looks like all of these values, except for 9.5, fit into this new range. And on the other end, we get to get as high as 24.8, which covers everything on that side. So now only one of the 50 items doesn't fit into this range. So 49 out of 50 gives us 98% of the data lies within 2 standard deviations of the mean, which at the end will compare to that 95%. Now finally, this says that 99.7% of the data will lie within 3 standard deviations. So that's the third part of this problem, the 99.7% part. We're going to use that same kind of formula, but now it's 3 standard deviations below and 3 standard deviations above. Plugging in what we know, and we're ready to go back to the calculator. I'll change the middle to -3, which gives us a bottom range of 6. And then if I change it to +3, I see the top range is 28.56. Now looking back at our data set one more time, we know, because all we're doing is just making this range wider, we know all these data values are still going to fit, and now so does 9.5. So all 50 of our data values fit within 3 standard deviations. So that's 100%. And now at the end of this problem, now that we've done all that work, all we're going to do is assess whether or not these 3 numbers, 64, 98, and 100, are close enough to the 68, 95, and 99.7. Now we get back to the gray area of statistics, where there's not an exact right answer of how close you need to be to these 3 percentages to be able to call it normal. Now, if these percentages were 50, 75, and 90, that's pretty clearly not normal. But they're not always going to be exactly 68, 95, and 99.7. And that doesn't mean they're not normal. My personal rule is that if the first 2 numbers are within 5% and the third number is within 2%, that's close enough for me. When it comes to getting credit on a quiz or a test, as long as you've done all this work and your conclusion and justification's not way off, I'm probably going to give you all the credit. So I'm just going to conclude that 64, 98, and 100 are close enough to the empirical rule percentages to call this normal. And all of this work that I've done up here is my justification for that conclusion. In this lesson, we learned 2 different ways to assess normality. The first was using a histogram. If your histogram starts low, ends low, peaks in the middle, and has no gaps with symmetry, then it would be a normal distribution. The second thing we learned about was the empirical rule. The empirical rule gave us different percentages for different numbers of standard deviations. Now keep in mind that the empirical rule talks about the population, and what we're dealing with is sample data. So we're not always going to meet these percentages exactly, but if our data displays percentages similar to the empirical rule, there's a really good chance that our population is normally distributed. If you came away with anything else in this lesson, write that down now. Otherwise, we'll see you next time.